What's up, everybody? Welcome back. Today we are working on dealing with manual memory management in WebAssembly modules. So the context here is we're working on this Rube Goldberg machine, right? Where basically like balls will go through these chambers, and eventually these chambers will be like hooked up together to form some sort of like cohesive machine, right? And the interesting part here is that these chambers, the balls are like controlled by like a external simulation. Like the gravity is applied to them. Their like collision between each other is collide, but the chambers are define their own like platforms and physics and stuff like that. So what's happening here is we have this like WebAssembly module, and he has like 4 platforms in him, and he's saying every time you step me, I'm gonna like move my platforms, and if I detect that a ball has hit my platform, I'm going to give like the correct physics impulse response to that thing. Which means that we have like the ability for any chamber to have like very, very, very custom behavior, right? It's like a very advanced scripting engine or virtual machine, right? I guess like it is a virtual machine, right? And so the idea here is that eventually people will upload WebAssembly modules themselves, and they will like I will go in and approve which ones I want and like kind of like put them in whatever order I want, but the chambers will all be written by like individual users. And so what I want to work on today is kind of like making that WebAssembly interface a little bit better, because right now it requires like a memory allocator interface to be part of it, and I think that we can get rid of that, to be honest. So kind of like the way it works, how is the best way to draw this? There's kind of like 2 contexts where this WebAssembly module is run. WASM chamber. One of them is like server, and he calls into him to say like run physics, as well as to say like save your like current state. Then he like kind of like forwards some of that state over to the client. The client instantiates the same WebAssembly module but inside your web browser, and he is going to like call load with the state as well as render. And so the reason that we have memory allocation interfaces here is because like the memory model of the chamber is you have like this guy inside him kind of has like this like big ass memory buffer. And like this memory buffer is kind of like managed by either the server or the client, kind of. But like from his point of view, he's kind of said, hey, I want this like, you know, this like 400 byte block of memory or something. Probably more likely like 64K byte block. And so what will happen is for us to like run physics on like a bucket of balls, right? We have like ball 0, ball 1, ball 2. For this guy to like apply some change to these balls, he needs to like write to the memory. And so what we do is like we like ask the WASM chamber, say like, hey, can you like give us some memory for these balls, right? And then we copy paste our balls into like WASM memory, run the physics simulation, and then copy them back out. And for the same thing for the save, right? We say like, hey, could you like give us a buffer for your save file? And then save, and then we ask them to save into that buffer. That's kind of silly, right? Because in reality, there's only a few things that we actually need memory for. On the client side, it's the same thing. For render, we pass in like the render canvas so that he can just like write pixels wherever he wants on the screen. And for load, we pass in the load buffer. And so really like all you really need here is like 3 buffers. One is like balls, right? Balls. You have like save buffer, which can be used for both saving and loading, and the render buffer. Now we can't like kind of like statically code, we can't like hard code these necessarily, because like the canvas size might change, and so how big this buffers might change. The number of balls that we feed into the simulation might change, but we could probably set like an upper bound on number of balls for the server when it loads, and so we could probably just allocate these things like one time on initialization. And so that's kind of what I'm thinking is like, I want to get rid of like the requirement of an allocation interface for this guy, which will make this simpler. Maybe we will just provide these 3 buffers and see where it goes. So I think what I want to do is I kind of want to work on a WASM chamber in C, where we just work with the WebAssembly memory pointers directly. Basically, we can just pre-allocate like these 3 things on initialization, just by like bump allocating. And then we'll see where that takes us. I was reading this pretty cool page when I was looking into this. I couldn't find any like official docs on like the WASM memory module, but this thing was pretty good. So surma dev thing c WebAssembly. If you just search up like compiling c WebAssembly without an M script, and you'll find this. But he kind of talks about in here, or they talk about, I don't really know if it's a he or a she or a neither. But there's this nice diagram where basically WASM memory, so they have like a data section, which is like basically your static variables, like your strings. Like if you type hello world, that hello world is going to live in here. Then they have like a point in the WebAssembly memory where they kind of like bisect heap and stack. So there's like a fixed stack size, and then the heap can grow as long as you just like keep reallocating this buffer. And so I think that what we can do is we can probably just look for this heap base symbol and just like allocate from it ourselves. That's kind of what I'm thinking, and we'll see. We'll see. So that's kind of the plan for the day. We'll see how it goes. We'll see how it goes. You could unit test chambers on submission to validate balls coming and go at the rate you want. Yeah, that's exactly part of the plan for sure. So I'm gonna like the first level is gonna be like size validation, right? So they're going to be maximum like 10K probably. We'll see how low we can get it and then kind of like work our way up from there. I'll probably make like 10 modules or something myself and just kind of see what types of sizes we can expect to set the upper bound. And then I want to instruction count them. So like I'm going to run a simulation, feed 100 balls into it, run the step function 100 times. How many instructions were executed in that? And then we can like kind of set some sort of like expected limit there so that we don't like let single modules just like destroy compute. And then yeah, I agree that we should make sure that within some reasonable amount of time, like it doesn't just eat balls forever. But I think that like there's some chambers that you might want something where like after 20 balls goes in, they go in, they all come out. You can imagine something like you have like a latch on something where you have like a scale here and the scale is like connected to some sort of like latch that opens a door over here or something. And like you kind of want the balls to like accumulate in here so that the latch opens and they all fall out or something, right? So I can see a world where you would want to support some level of ball eating, but not a lot, right? And we can always, there's also going to be like human validation as part of this as well. So if it's something that looks bad, then we could just nuke it from the simulation. Not the end of the world. Not the end of the world. Okay, so let's see. So let's start by looking at our simple 2.c. So this is our only example of a C chamber. And let's look at the build script here. So when we build this thing, we kind of manually say, these are the symbols that we want to export. And so this is the entire interface of our thing right now. Init, dinit, alloc free, save, load, step, render, save size. Now what we should be able to do is replace this alloc free with like getters for where in memory the save buffer, load buffer, and render buffer are. But I think before we do that, I think what would be kind of fun is to just implement like a bump allocator that just like continuously bumps heap memory until we run out. And that will crash at some point. But it should let us get like a few frames in just to prove that we understand like the memory model. And then once we have that, then we can kind of work our way backwards. So I want to look at, what was it? I forgot already. Simple 2.c. So I think it's easier to start in C here. And this guy's saying you can just kind of like access heap base. So like, let's just see if this is correct. If I go in here and I just slap this in here, let's maybe on init say, I think we have like a logging function that we can call. I think it's a, let's see, chamber simple zig log wasm print. We seem to have lost it. But it's here somewhere. Also, just give me a second. It heated up, and so whoever was complaining that I wear a sweatshirt all the time is correct, and I'll be right back. I'm gonna switch to t-shirt. Yo. Okay. So I know that we do support, or we had at some point a like logger function. Log wasm. Yeah, we have this thing. So he takes in, what does he expect? He expects an input of offset and length, and then he's going to log that thing as a string. So I think that in our simple 2, let's start by trying to get our logger function to work. So we can say it's something like, fuck, where does this get passed in? This gets passed in here as log wasm func. Do we have to like name him in any way? I see. So he's just kind of assuming that any import, any required import is the log wasm function. Okay, so we could really name it anything we wanted, but we'll name it something. So it's like log wasm, and he takes in int offset and int len, and this is extern. And then we should be able to like compile this. So if we just go in here and we say like log wasm hello world like 10. How long is hello world? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this I guess we can say is a char star. Well, the link time casting we call it. So this compile. No, because undefined symbol. So I think that we can just allow for undefined symbols. Wasm ld undefined symbol. How do we wasm ld import function. How do I do this? This isn't what I want. Clang wasm import function. Surely this is possible, right? You can use import module, import name, or you can pass allow undefined. Let's try just passing allow undefined and see what that does. Linker allowed undefined version. Let's just try this and see if this does what I want. Allow shared lib undefined, I assume is what that means. He might get mad, but we'll see. No, he doesn't like that. He does not like that. Force as undefined in the symbol table, thus forcing their resolution by the linker. No, I want it to like allow undefined. Is there like an argument in here? Can we go to like the Zig source code and see if they pass that allow undefined flag anywhere? Oh. Ah. Okay, wasm, it was something wasm import symbols. Where does this come from? Source link wasm. Okay, we're gonna look for that. So in our build script, this is an executable which has options like this. Was it wasm link? Fuck. It was in link wasm zig. Allow undefined. Yeah, it was import symbols. So this comes from options, linker, import symbols. And import symbols, linker import symbols, import symbols. Okay, we're gonna look for that. So in build, we can look for build. Fuck. Ball machine build zig. We can look for like something like chamber import symbols equals true. Hell yeah, this is the one. Let's see. How would compiling with undefined symbols even work? So the idea is like when you have shared objects, you're kind of always working with oh fuck me, I'm in the wrong folder. You're kind of always working with undefined symbols, right? Because like you say, hey, my shared object has this function foo. I would like to call the function foo. And where the function foo is, like its memory address of that function, does not exist until runtime. And so what happens is you just in your object, like in your table, you just have like a bunch of like how do I say this? Kind of like my mental model. Who knows how correct this is, right? Is that you have like main somewhere in your executable, right? And you'll have like in main you'll have like foo, right? Now this is going to resolve to some address. And I think that what they do with dynamic linking is that somewhere you just have like pointer foo is equal to null, right? And then you like load shared object. And in here, they do like foo is equal to shared object dot foo, right? Hand wavy. Right? So you kind of like, you can just do the same thing here where our function, like it's undefined at link time, but we're hoping that somebody will set that function. And so I think that if I understand this correctly, the WebAssembly runtime will kind of do like a similar thing where it will, if I load that function, it will set it for me. I think. But there's only one way to find out, and that is by running it. And I just realized that loading these chambers is actually a pain in the fucking ass now, because we have to actually add them to the database, which sucks. That's awful. That's really bad user experience. Okay, for now, let's do this. We'll go git checkout -b chamber testing and git log. We'll rebase from here onto his parent, and then we've just gone back in time, so we don't have to worry about that anymore. We'll come back to this later, and we'll just run with -- chamber, and the chamber will be zig out bin simple2. And hopefully this works. We'll see. I don't want to run GDB. Thank you very much. Oh, okay. So we got our hello world. That's a really good sign. So it looks like we have successfully figured out our logging thing, and now we can go back to the fuck. Where am I? We can go back to doing whatever. Thanks for explaining. I wasn't aware that using dynamic libraries is basically using undefined symbols. Well, I mean, like, so when you like launch a dynamically linked executable, like the loader will inject all of that information for you. So like by the time that you call main, it's essentially like they're all there. It's just you have to go through some like runtime validation, because like there's like, I think it's called like address space randomization, ASLR, address space layout randomization or something, where like the Linux kernel intentionally changes the address of things every time you load it to make things like a what do you call it? Like make exploiting harder, right? Because like now you can't just say, oh, I have access to memory, I'm gonna write this specific address where I know that function is. It's like, well, now I have to find the function first, which makes things a little bit harder. Not like infinitely harder, but a little bit harder maybe. Okay. So we have a way to log stuff now. And I guess we do something with that. I don't know what though. So we wanted to try seeing if, I wanted to just log heap base. Which is going to be a pain in the ass. Oh, man. Like, do we have to write our own address to string function? I guess we kind of do, huh? I wonder if, like, we could just try to, like, print to a buffer. Oh, that's awful. That's fucked. I guess we just write our own, like, toString. Print int. Print num. Gross. So how do you do this? You do, like, you want, like, the biggest number to go on the left. So you do something over 10. So first we need to like determine how many digits it is. which is kind of like, so 2, like in base 2, you have like 2 to the 3 is equal to 8. So this is 8 is represented by 4 digits. So you need to do like log. You need to do like log base 2 to figure out how many digits you need. Or in the case of base 10, you need log base 10 to figure out how many digits you need. Or you could be stupid and say size t num digits for a given integer is going to be count is equal to 1, and while true, x is divided by equal by 10, and if x is equal to 0, we return count. Otherwise, we do count plus equals 1. And there's no true without a stood bool. And then we can get the number of digits. So here we take some number x, and we say num digits x. And what do we do here? We say something like each digit is going to be that thing divided by 10 that many times. So we're going to say like outbuff. We're going to say that like the maximum number of digits we can print is like 20 or something. So if num digits is greater than 20, is there any like assert false? I don't know if this is legal. I don't know if this will compile to the right thing, but we'll try it. And then I guess this is gonna be 21, I guess. We say out this is equal to 0 or something. 0 initialize the whole thing. Then we just go for int I is equal to 0, I is less than num digits plus I. Out buff num digits minus I is equal to x% 10, and then x divide equals 10. And then we print the thing. So we just say log wasm out buff for num digits. There's probably like 4 off by 1 errors in here. But we'll see those in a second. So here let's just say we're gonna like log wasm print num 10. Let's just see how fucking bad we are at this. Okay, assert file not found, so that's super cool. Is it like stood assert? No, fuck off. Okay, how do I like wasm panic? Like, I like, there's gotta be like a clang wasm built-ins. Here we go. Is there like a trap in here? Trap? No. Atomic rethrow. Oh, throw? Okay, wait, that sounds good. That sounds like what we want. Built in. Is there anything else that looks more like it? What was it? It was built. Fuck. Built-in wasm throw. Like if I just do this, I wonder what that does. Of course that doesn't exist. Fuck. There's another shot. It was worth a shot. Clang. Because like I know that like wasm what instructions. There's a way to just like fucking like trap your shit. Like I think there's something like can I get this all on one page so I can just like fucking search it? As PDF, I guess. And then can we look for instructions? I think there's like trap? How did we can maybe look in the we can do this. We can do this. We can look the Zig version. And in here we can say like unreachable. And then we can Zig build. Oh, oops. Let's fix that here. And then we can wasm to what? The simple wasm. And look for unreachable. Oh, it is just unreachable. It is just unreachable. Okay, so is there like a clang wasm built-in unreachable? Do you insert that? It can't be longer than 20 characters. I mean, I just want to be able to do it. Built-in unreachable? Let's try that. Nope. Unreachable. Oh, it does say that this exists. So let's just try this and see what happens. Okay, let's try 0 here. And just see if that actually traps. Because I want to... okay, good. Internal error on init chamber. That's a good sign. And if we change this to like 20, it doesn't trap, which is really good. It doesn't print the number, but that's really good. So we could do something here too, where we say log wasm high with 2 digits. And we see that we do run this twice, so we should get a thing that's 2. Oh, and our problem here is that this shouldn't equal to x plus 10. This should be x plus 10 plus 0. Because I'm an idiot. Okay, so we got the number 1, which is bad. We're off by 1. So here, num digits. This goes from 10. Divide by 10 is 1. So we should get a count plus equals 1 here. And we do, because we see this high printed twice. So we do get 2 digits. So we should see... Maybe this has to be... Maybe we have to write 3 here, because it's null terminated. Here we print out a string of data. Data is this thing from offset plus length. Wasm slice is... It goes from offset to offset plus length. So this should do it. Num digits minus I. So here this is 2. Minus 0 is 2. Oh, this should be minus 1. There we go. That's why. There we go. Okay, we see the number 10. And if we write the number like, you know, 1, 2, 3, 4, 5. There we go. Sick. Okay. We did it, guys. We did it. We wrote a thing. Took a second, but we got there. Okay. So now we should be able to print the heap base. Cast to an int. 0. That's not good. Unsigned car star heap base? Yeah, that's really bad. That's really bad. So what are we doing wrong here? Oh, ampersand heap base? That probably makes more sense. So we take the address of heap base and we log that. Okay, that seems reasonable. Maybe. I don't really know. I don't know how to validate this. So I think that we have heap base, data end, and max memory. So if we look at data end as well, we might be able to get a clue about like the stack size from here. Uh, very, very short, which is concerning. Like, how do I specify, like, is my stack size like intentionally like that's like what, like 8 bytes? No fucking way is my stack 8 bytes. The stack starts at data end. This heap starts at heap base because the stack is placed for. Well, okay. If we look back at the globals of our thing, so this makes more sense. How are we building this again? We are. What are we doing? We're just running whatever Zig wants to run. I have this thing here though that I can try running and see if that gives me something else. Okay, so this is gonna be run from the directory with the chamber in it. Undefined log wasm. So here we want to do wl allow undefined is what we said. I already forgot. Allow undefined. Fuck. Okay. I guess the Zig linker doesn't support that. What's the current problem? We are just trying to understand where our heap starts in WASM memory, and we are just slowly poking our head, trying to figure out. Yeah. So we're right now we've got a way to print from our WebAssembly module, and now we're just trying to understand what we printed, like the heap base and this where what we believe to be the stack is like way too small. So we don't understand something. I wanted to look at, and then here we're trying to manually compile this thing so that we can try changing the stack size and stuff, but the linker flags aren't working the way I expect. So we can look at maybe like no entry. This is going to be in here somewhere. So here, these are like the linker flags they support. And we can look for allow undefined. They don't have. But what did we set it in the build script? In the build script, we set import symbols. So does this have that? Ah, he does. So I can pass this to, I can just pass import symbols to the linker flags as well. There we go. And this creates a WASM thing. And what was I trying to test in here? I wanted to see if I could like change the stack size. So it can be like Zig WASM stack size, maybe? Doesn't the compiler automatically calculate the size of the stack and minimize it? That seems possible to me. I want to be able to like manually specify it. Here we go. So this guy's saying you could maybe do this. Well, I don't know if that's what he's saying because I didn't read it, but maybe. Okay, stack size. Okay, we do WL stack size equals this. No? Where does this stack size come from? If starts with Z. What is, okay, where are we here? Linker arcs. So it's Z stack size? I see it in here. Am I high? There we go. There we go. Another comma. Another comma. So now if we run that thing, so we should be able to run this from wherever we just compiled that thing, which was source chambers simple2 WASM. Maybe the stack grows in the other direction. Right? That clearly changed something, right? That changed the... Yeah, that definitely changed something. It's possible that, like, the zig linker is not necessarily doing the same thing that this guy's saying here. Where he's saying that the memory grows this way. Maybe for us... I wonder if we can, like, log the stack pointer in some way. We could, like, go down a function and see which way the stack grows, which would be kind of interesting. So we could do something like clang stack pointer. Can we, like, clang print stack pointer? Do I have to drop to WebAssembly to do this? Data end and heap base. I mean, that's what we're logging right now. These two things are data end and heap base. And if I understand this, they're saying that my stack should start at the same position as... Oh, you're right. Sorry, you're right. It is expected. I was thinking that my stack starts here and grows towards the heap. You're right. They start right next to each other and the stack just grows down. Okay. Yeah. I think that is right. You're right. I was confused. And so the fact that the heap is just a little bigger than the stack actually does make a lot of sense. Which kind of means that we can go back here and we can, like, try making our little bump allocator. So our bump allocator basically says, well, do we have max memory as well? We do. So this is... Where do we get max memory from? I think I saw... Okay, so I was looking at this, like, C allocator wasm malloc here. And they, at the very least, have this thing that they call. So maybe we look at this as our way of telling where the heap ends. We can say print log wasm max memory, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then maybe put this... That's fine. And then we print whatever the fuck this thing was. Where did we get that from? It's from wasm malloc. Built-in wasm memory. So here we print heap size. And page size, I think it's just 64K. Yeah. I think that's just, like, hard-coded in WASM spec. So this is how many pages we get. We can maybe, like, look at the docs for this. Built-in WASM memory size. Like, surely somebody will tell us what this means. Here's a link. Query the amount of memory size and increase the current size. Note the memory size is not... See, it must be sequence of... Okay, it doesn't tell me what the fucking unit is. I mean, we can tell from this allocator that it is in pages, but it's just kind of annoying that we have to do it that way, but that's okay. So let's maybe print it without the page size to see. So here we just want to run like this. So 17 pages. Which lines up with the fact that it needs to be bigger than these numbers. So it looks like our heap size initially is not very big. Do you want to make an allocator that manages the entire heap? I mean, for now, yes. I mean, this is just kind of like a stopgap, right? I think that what's going to end up happening is we want to get to a point where we don't need a memory allocation interface at all, but we can just kind of, like, in initialization of our chamber, specify addresses for the different things that we care about. But I'm trying to do it in, like, stages. So stage 1 would be make a really shitty allocator just to test the concept so that we can, like, do it without changing the existing interface. Yeah, okay. So 111412 minus this. So what's this minus this? We can just do that. Heap size minus int heap base. Oh, that's not too bad. That's one page. One page. So 65K. What's wrong with the stdlib WASM allocator? So one, I think that we don't have access to a WebAssembly allocator in like the Clang freestanding binary. I think. And two, it would be nice if we didn't have to worry about memory management from like the external API. I'm trying to basically like reduce the amount of complexity that is necessary in order to get like any chamber running, right? I want the simplest chamber to be simpler, and having to do memory allocation as part of your interface just like guarantees extra complexity, if that makes sense. Okay, so for now, we can, in an example, we can do something like, here we're gonna have some sort of structure, which is gonna be like app state. And in here, our only thing that we're gonna have is the memory alloc pointer, I guess we'll call it, which is just going to be a void star. This is going to start at okay, we are going to like make the alloc pointer is a void star cast of heap base. Then we're gonna increment this. Maybe it's easier to think of this as a car pointer, because that means that we can do, I don't know how like integer math works with a void pointer. Okay, yeah, that makes sense. It's not allowed. That makes a lot of sense. So let's work with it as a car star. What we're gonna do is the first thing that we need to allocate is the first thing that we have to allocate is ourself, right? So app state is equal to app state is equal to alloc pointer, and then our alloc pointer plus equals a line of size of. I don't know. I'm sure this is breaking some rules, but we just want to start somewhere. Dude, this is crazy. Could you show an example of uploading a file in React using use mutation? I have doubts about this, and I'm implementing and having difficulty. Dude, what? You're using me like ChatGPT. First of all, I've never written React in my life. Second of all, like, do you think that it makes sense to just come in? Like, I'm talking to like, 80 other people right now, more when you consider the VOD. Do you think it's reasonable to just be like, you know what? Fuck all of those people. I want what I want. Like, no, that's not reasonable. No, I'm not gonna do that. But that's like, I don't think that you should expect people to do that either. That's a crazy ask. This isn't for, the stream's not for you, right? It's for everybody. That's insane. Guys, don't do that. It's crazy. Okay, sorry. Just ask ChatGPT, man. Like, you're using me exactly like somebody would use ChatGPT. Just do it. Sorry. Anyways, not important. Average Twitch chatter. Yeah. Incompatible pointer type. So here we're gonna cast this to an app state star. Okay, and then we return alloc pointer here. Can I rent this stream for an hour then, kind of for myself? I think that probably I just wouldn't do, like, I want, like, surely there's an amount of money that I should want to do that for, but like, I'm really big into like, if I don't want to do that thing, then I just don't. And so I don't know how much money you would have to pay me for me to want to. Stream auctions, yeah. Okay, so then our app state alloc pointer is equal to the new alloc pointer. And then we return our app state. Okay, now theoretically, if somebody, when they call alloc on us, this doesn't take an app state. So really, we actually shouldn't do it this way. We just make a global alloc pointer. Static car star alloc pointer. So here we still return null. Our app state doesn't exist. Because of the way that our alloc interface works, it can't be tied to an app state, which kind of makes sense, I guess. And so then we will just here, maybe what we'll do is every time somebody calls allocate, we will say to ourselves, log wasm. Maybe we'll say, can you do like, what's like the easiest way in C to like get the length of a character array? Like, that's a stupid question, but like if I do like car s is equal to logging or allocating memory like this, like then I can do s size of s, right? That's allowed, right? Because but this only works if this is an array, which I think that this makes it, right? If I did like car star s, then I would have to do strlen. But yeah, somebody's saying strlen, but it's like, you know, I think concept of runtime counting the characters when I know them at compile time pisses me off. But you're right. So car star red, giving you size will give you the size of plus a zero terminator. Yeah, that's a good point. That's a good point. Thank you. So this is going to be ret is equal to alloc pointer, and then here we just say alloc pointer plus equals size, and we are ignoring alignment and fuck off. Shouldn't Zig automatically reduce strlen to be a number because of LTO? I don't. So I think that here, Clang is responsible for compiling our C module. With LTO, I don't think LTO does stuff like that. I could be wrong, but I was under the impression that LTO just does like cross-module inlining. But I don't actually know, so I could be totally wrong about that. I guess it would make sense if you have like some function that is like resolvable at compile time given the inputs from another module, then it would make sense that LTO does that. But I don't actually know. Ever I've worked ever has LTO disabled because it's so fucking slow. Okay, let's just see what happens if we do this. Okay, so here probably what's happening is after like very few steps, this is failing. No, it doesn't actually like immediately chamber step failed. That's surprising. So this is here. Step fails. That's interesting. Oh, because I didn't return here, probably. No? Can we maybe like built-in unreachable here again? No, fuck. I just want to like maybe call this one time. Alloc pointers never set to heap base. That would do it, huh? That would do it. That would just kind of fuck up everything. Can we just like car star this? That's fine. Okay, there we go. Okay, wait, that's good. So here, we want to make sure that allocating memory here, we need to make sure that we limit this as well. So if alloc pointer is greater than or equal to, did we lose our calculation of max memory? We did. It was built-in wasm get, fuck, I don't remember. built-in WASM memory size times page size. Return null. And we'll say here, allocation failed. So size of failed -1. Then here we'll say car failed is equal to failed to allocate. There we go. Can we do like in here? Seems fine, seems fine. So here it's like if alloc pointer plus size is the failure here. And that's fine. If that builds, we'll be happy with it. Oh, okay, cool. So we do see that we like allocate for a little bit and then fail. So maybe we can just kind of like bump this thing up. Like, can we like 10x it? Or yeah, let's look at how we do in WASM memory grow, just that we have enough time to see if it's like behaving a little bit sanely. So there's a grow in here somewhere. So here, maybe let's just like kind of immediately be like, make me big, please. So I assume this takes the number of pages that it wants. So we saw 17 at the beginning. So can we just be like 170? And I'm assuming that the first index here is like which memory we're looking at. WASM, like there's like proposals for multiple memory blocks, but I think that the official spec right now only supports one memory block. So we just put a 0 in there every time. Oh yeah, that's a good sign. That's a really good sign. Let's here maybe log the memory size again. So we can say, well, we don't even have to. We don't have to. Let's just zig build and look and see if it looks okay here. It does not look okay. Which is maybe not good. It's kind of surprising, actually. Kind of surprising. So maybe we run this again, refresh, and look at here. Can we look at like the console here? So in alloc. Oh, fuck. Right, because when we try to render to the canvas, it's big. So can we just make that number like even bigger? Okay, like let's just double check here. So if we do like 65 times 170, that's 11 megs. Because that's I guess what we can do is we can do free and we can say if p is equal to alloc pointer minus equals last alloc size. And then here we'll say static last alloc size is a int equals to 0. And then here every time we alloc, we'll just say last alloc size equals size. He still doesn't like it, I think. It's kind of hard to see why. Yeah, so this is in chamber JS70. We're getting an exception here. So is it just that we need to go even bigger? What is like canvas width times canvas height times 4? So this is, I think it's, I can just look. Where do I define this thing? Width. 600 by 450. That is 1 meg. So we need like a few more pages, I guess. No, wait, hold on. 65 times 170. We should have 11 megs. Maybe here we'll just write log wasm decreasing memory. Fuck, we have to do this. And then s size of s. Okay. -1. And this is a car here. Character? Character. Car. He doesn't like this because we actually didn't support const cars here before, I guess. Okay, so do we see the same behavior in like... Oh, I guess we might not. Like, we need to check if we hook up log wasm in JavaScript. I think we might not. Yeah, it's fucking broken. That's okay. We can just fucking hack it for now. Var chamber is equal to null. Then on here, we will just say, when we load a chamber, we will say chamber is equal to obj. That should fake it good enough for us to see something. Allocating memory. And then he immediately unreachables. What the fuck? Let's see. We can maybe go into our chamber. And when he allocates, like, why is he... What's the problem? What's the problem? What's interesting is he's actually... He's actually hitting an unreachable. Which I think this shouldn't do. Let's just hack it for now and return alloc pointer here. You can debug wasm in the browser. That sounds fun. How? Uh-huh. Oh, but this is just, like, it doesn't give me, like, the C code associated with it. Which is kind of the part that I would want, right? Here it doesn't even show wasm. I'm sure there's some way, but it's probably tricksy, so. Okay, allocating memory. We can just start, like, bisecting. So it actually could be that this allocation succeeded, and then something else went wrong. So here, let's say allocation success down here. And then we can do log wasm success. And in reality, we could do like a little macro to make that a little easier for us. But we'll see. Ah, okay, so that allocation is succeeding actually. So this is failing. So I don't understand. This is failing here, but we're returning a valid number. So how is an unreachable happening? Oh, because I'm a fucking idiot. Because I am a fucking idiot. Still no good, though. But, I mean, that looks a little better. So, yeah, he's still failing here. After his first allocation success. Return. Like, am I stupid? Whoa. Why isn't he printing the number? Is this? Oh, maybe we're fucking hitting a trap here. Ah. Okay. That's a good clue. That is a very good clue. Oh, fuck me, because we have to do this on load as well. Fuck, because in the fucking... Oh, because in the In the browser version, we don't call init on the module. We call load on the module with some state. That's why. But he's still fucking broken. He's still at address 0. What the fuck? Here can we say, like, is heap base just not defined here for some reason? Can we do, like, loading, 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 loading. We should see that here. We aren't seeing it there. Oh, I see. So, okay, here's what we're going to do instead of this. Instead of trying to set the alloc pointer here, we are going to say on alloc, if alloc pointer is equal to 0, we set it to alloc pointer equal to car star heap base. That makes way more sense. Then we don't have to worry about this. And we'll also grow the memory. Yeah. Hey! Okay. It's doing something. Okay, that's working. Wait, that's working. That's good. Okay, so we have our, like, really shitty allocator. It's like, it looks like it's doing something, which is good. So we have a good understanding, or I won't say good. We have a decent enough understanding of this, like, heap stuff to basically, like, ditch this WASM malloc allocator and do it ourselves. And that's working fine. Now, we have this problem where we're consistently growing in memory, but we don't have to worry about that if we now change our API to say that we are going to just hard code a few memory addresses on start, which is pretty good. All right. I'll take it. We'll take it. Okay. So what is next? We need to look at the API of these chambers. How does a WASM run? WASM time? On the server, it's run using, I think we have to, like, WASM time, yeah. I couldn't remember which framework we were using. And then on the client, it's using just like Firefox instantiate streaming. Okay. So I guess, like, on initialization of the chamber, what are we going to say? We're going to tell it the maximum memory usage of a couple things, I guess. And then we will then ask it for those components, which I think is fair. Yeah. Okay. So what does that look like? On init, we will just feed it some parameters. And we expect those parameters to be the max physics max num balls for the physics simulation, because that's passed in here, right? And then we also have max canvas size. Yes. And then we could maybe just say that the statically we say that we have a struct ball star balls memory, and we just do this for canvas memory. And this is now going to be like a 32 star. And then the save memory, this is going to be a UN date star. Now in our case, we actually have no data to save, so we don't have to worry about that. We just have to make our balls and canvas memory. So we can just say that we have if max num balls plus max canvas size. We're gonna have to do some like alignment bullshit here later, but for now we're gonna ignore that. We're gonna say if this is greater than, we'll make a function here that's like, this returns a size t, and it's like memory heap size, I guess we'll call it. And this will just do whatever the fuck we were doing down here. Right, just return this. Then here we can say if this is bigger than the heap size, probably greater than or equal to is more correct, then we are going to ask for that many pages. So we're going to say page size over this. We'll say const required memory, max on balls plus max canvas size, max canvas or required memory. And then, okay, so say required memory is like 2 and page size is 4. We need 2 pages. If max memory is, required memory is 3 and page size is 4, doing page size over required memory will give me 1 as well. Say required memory is 7, page size is 4. 4 out of 7 is going to be floored. It's the other way around. Required memory over page size. Yeah. Why are you writing the allocator in C and Zig? I think we'll do something similar in Zig as well, but I wanted to get the C one out of the way because it feels like the C is going to be minimum complexity, I think. So here we need to do like a roundup here of required memory. So const size t required pages is going to be required memory over page size, but we add page size minus 1 here. That's how you do a roundup, right? So if this is like 7 and this is 8, this is gonna be so this is 8, this is 8. This goes to 8 plus 7, which is 15, divided by 8 is back to 1. But if this is 9, then this will go to 2 because that'll turn to 16. Yeah. I think that's right. Okay, so in this case, then we'll just say built-in WASM, was it memory grow to the required pages? And then we just say we say this needs maximum balls times size of struct ball plus max canvas size times size of int32. There we go. Then here we say balls memory is equal to, we'll just set this to like heap base. And then we will say canvas memory is equal to balls memory plus, and we'll maybe split this up. So we'll say const balls required size is equal to this. Boom, boom. Boom. So this is going to be balls memory plus balls required size. And then here we'll do like a fix me alignment, right, for both of these, because we will have to align them in some way. Okay. I think that'll probably work. And then instead of alloc, we're going to say, could you give me a pointer to balls memory And here we will just return balls memory. And we'll have another one for save memory, which in this case we return null because we have nothing to save. And then we have another one for canvas memory. Return canvas memory. Okay. Then we delete this alloc function. We delete the free function. Save size is also defined here, so that still is valid and useful. Okay. So now we should be able to we were going to build this thing and try to load it, and it's going to fail. Oh, well, first it's not going to build. So, because we didn't actually give data types to our things because we're fucking in ZigBrain mode. Okay, so that builds now, but we init failure trying to find the alloc function, which makes sense. So we can just kind of like work through these failures. So alloc function doesn't exist anymore. Free function doesn't exist anymore. Then this alloc wasm function and free wasm function go away. Save size stays. And now we're going to try to alloc wasm, but instead of trying to alloc wasm, we'll just say, could you give me the save, what do we call it in this simple to see? We called it save memory. Which means that we need a function to wrap that. Which is going to return probably just like an I32. Probably failable. Right, because everything that comes in and out of WASM is I32s, if I remember correctly. Then we should be able to do something that's basically the same as the save size function. This is a WASM chamber probably. So he has a context. He's going to call this thing, and he's going to call this save memory function. He's going to get no inputs and one result. If we fail, we fail. If it's not either two, we fail. But yeah, that's chilling. So now we just have to find that save memory function. Memory function. So on initialization, instead of looking for alloc, we say save memory function is save memory. And then we might as well just hit the rest of them here. So we'll just say save goes to fuck. A simple, it's balls save canvas. Now we're actually not going to have to use the canvas memory here, but checking that it exists is like important here. Because it will make sure that we like validate that at least the function exists on the server side. But we don't have to write it down. I think we don't have to free these functions, so I think we're chilling. Yeah, they're just kind of like sitting there. So here we'll just say, discard that thing. Then we replace the alloc function free function with save memory function. And balls memory function. Sick. 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 Okay, so this guy calls save memory. He doesn't need to free it. He doesn't need to pass the... He actually doesn't need to pass the memory in anymore. Which is kind of interesting. He only needs it to... So when we call save, since we know where it's going, we actually don't need an out pointer, which is kind of interesting because we can just write to that memory directly. And so here, we actually just call this stuff, we call this stuff after we call save, which is kind of interesting. Yeah. Yeah, so here we say, like, here's the save data, here's the save size. I guess we still need to do this, like, casting shit. So this comes here, this comes here, boom, boom, boom. Then up here, we don't need to call two parameters here, which means that this is an input, a singular input. So this kind of turns into this. Oops. And then this becomes input and 1. Okay. Good, good, good. We're getting somewhere. He called save memory, gets a lot of slice, he dupes the stuff out. What's kind of interesting now is we actually technically don't need to duplicate this because like the WASM memory is going to be static, although I guess maybe technically could like grow internally, and so we shouldn't really rely on that necessarily because after a WASM memory grow, maybe that memory becomes invalidated. So sure, we'll continue duping it out. Fine by me. Okay, so kind of the same deal here needs to happen on the step function. On the step function, he previously took in a balls pointer. We don't need that balls pointer anymore because we know where they're being written to, which is kind of interesting. So this becomes, for I know num balls, ball, this becomes balls memory here. Then everything else is the same, which is kind of weird. Okay. Cool. Then our step function now, he just takes out this balls pointer. He becomes an input of 3 arguments instead of 4. Which means that this 4 turns into a 3. We do not have to call... we don't call this alloc WASM anymore. But we still do need to get the balls pointer. Which means that we have like const balls pointer is equal to balls. What do we call the other one? We call it save memory, so we call this one balls memory. And then save memory and balls memory are just gonna look like fucking identical, except that this is gonna use the balls memory function, but everything else is exactly the fucking same. But we will move this over here to be right before step, because that's where it makes sense to live. He is going to call... Yeah, so you have the balls pointer. All of this kind of just makes sense. We're chilling, yeah. We're chilling. We don't compile yet, though. So this is ball undeclared at simple2 108. Did I delete a ball? Oh, ball was the input thing. So ball here, everywhere where it says ball turns into balls memory. All right. Free function doesn't exist, which is intentional. So get that fucking shit out of here. Alloc WASM still trying to be used for load. Ah, because we do use the load function. So chamber simple2 load. This doesn't actually have to take in anything now. We just say, hey, we're loading from the save memory, which means that here we call save memory. We don't use it for anything. And the load function now takes 0 arguments, which is very strange. Very strange. But makes sense. Cool. Still not working, but we're getting close. So incompatible pointer types here. Right, at simple2, line 65. This guy is adding to balls memory. So this actually has to be a car star balls memory plus balls required size, which will turn into a int32 star like this. Which is fucked up, but it's fine. It's fine. Undeclared identifier ball. I missed another one at 109. This is a ball like this is balls memory. Okay, balls pointer at WASM chamber 229. This has to be try, I guess. Makes sense. Okay. Fuck. Init failure. Save memory does not exist. Oh, because in our build script, we have to change our exported functions. So alloc free turned into a save memory, balls memory, and a chamber memory. This. Okay, close. We are failing on canvas memory. Right, because it's not chamber memory, it's canvas. We're getting closer, we're getting closer. And then probably initialization will fail because we didn't set the max sizes. So yeah, init chamber fails, which is fine. We just need to adjust the init chamber logic. So here, we need to give it some inputs. So where is an example of inputs? Here. Okay, so here we say that we have inputs is going to be, I think it was 2 inputs. One was the maximum canvas size, and one of them was the maximum number of balls. So here we'll say the first thing is the number of balls, which is going to be, I guess we'll just pass it in here. Max balls is a U size, and we'll just do like a this. Yup. And then inputs 1 is just going to be 0. We are never rendering to a canvas here, so we don't have to worry about it. Okay, so now when we call simulation zig 31, we're going to use num-balls here as our input. Yup, okay, so we are still internal erroring at init chamber. Surprising to me, because here we're not using the inputs. That would do it. Okay, it's running. That's a really good sign. Really good sign. So now we should be able to get away with like going. If we try to render this, if we try to like use this, it's gonna break because the JavaScript side has not been updated to use the new interface. But we can fix that as well. So that should make a lot of this stuff easier as well, actually. So here, this is gonna be chamber memory. Boom, 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 boom. All of this stays the same. We load with no arguments. Yup. We don't need to free here. Where else? We use this for pixel data here. So this is the chamber memory. And okay. Okay, yeah, that's fine. And then all we have to do now is initialize this when we make it. So we now are saying we will call init even if we're going to load. So load chamber. This comes from render from this chamber. So I guess on init here, when we construct our chamber, here it makes sense to do something like chamber init with a number of balls is 0. This canvas width times this canvas height is kind of the max canvas size. Because we're never actually doing physics simulations here. So initializing with 0 there totally makes sense. So that's kind of interesting because you could get away with maybe just saying like you have one memory region, but I think in the future I'm planning on doing some client-side simulation as well, so I think it's okay to leave this like this for now. Is that really it? That could be it. We'll see. No. Chamber init is not function. Really? Oh, right, because it's a fucking chamber instance exports init. Of course. Of course. Of course. Still no good, huh? Chamber memory is not a function. I did it again. It's a canvas memory. No good still? Why? Chamber memory is not a function? I fucking fixed that. Did I not? Oh, I did it again? Oh, because this is supposed to be saved memory. I'm just ding dong. Ding dong! Dingy dongy. Out of bounds, uint clamped array on an array buffer. That's interesting. That is interesting. Chamber pixel len. Okay, let's go that. So we did width times height times 4. Do we do that in simple 2? Max canvas size times size of int32. So we should see a required memory of that is correct. Oh, required memory is greater than or equal to heap size. This should be minus heap base. And then the required pages. Yeah. Oops. So here we subtract heap base, and then the required pages is I guess this is no, this is plus this. Yeah. So we have this much memory that we need, but that has to start at the heap. So then all of this kind of just kept and works for free after that. There we go. Wait, it's fucking working, guys. Let's go. Oh yeah, that's fucking sick. That is sick. So it looks like, at least in like the uber simple case, that this is working. And now we kind of want to just like check that more complicated case is working. So we're gonna update the platforms library. Because that guy actually has state that he's like shipping between the client and the server, and so then we'll make sure that we test like the save load interface there as well. Okay, so here, let's go to platforms Wisloan. Platforms Zig. Here we go. And he is going to do the same shit. So we're going to take our save. Okay, on init, we take in the max balls is going to be a usize. Max chamber size. Max chamber pixels is also going to be usize, right? Then here we're going to do the same thing where we have balls is going to be a variable balls. I guess, yeah, variable balls is going to be a const ball undefined. And chamber pixels is going to be a bunch of int32s undefined. I32s undefined. U32s undefined? That seems probably nicer. We're gonna say balls is equal to, here we can just use the WASM allocator. We don't have to write one ourselves. We can use the one if we want. So we can just say stood heap WASM allocator alloc max balls. Yeah. Catch return null. We do the same thing for the chamber. Max chamber pixels. Yeah. Super easy. Super easy. Nice. Oh, and here we can call it plugin alloc like we were everywhere else. Sick. And then here I guess we plug in alloc.destroy balls and plug in alloc.destroy chamber pixels. Except these are not destroy, these are freeze. Hell yeah. And then we just need to change this. So save. Oh, here we also have to allocate the save memory as well. So save size is 20 here. So we kind of cut paste this up here. And we just say var save is save size u8s. And we don't even have to allocate anything for those. Those are just like kind of like hard coded in static memory, which is kind of sick. Super sick. So this is just goes to save. What did I call it? I called it, I should call it like save data or something. So it doesn't name collide. And then just when we write the save, we just write it to save data here. When we load, we just load it directly from save data. I think I fucked something up here. Hold on. Yeah, like this, like that. Oops, oopies. Yup. We do the same thing here. Load doesn't take anything. This becomes save buff turns into save data. Yup. Then the same thing happens here, where in the step function, we no longer take in balls, we just use our balls memory directly. So balls. Oh, in fact, it's already defined here, so we don't even have to rename anything. Sick. And then again here, pixel data here turns into something. Something. Am I high here? I think I am. I think this should go back to stood. Keep wasm allocator. Because I think this plugin alloc is actually doing a little more than we need it to. So we kind of do this. All of this stuff is also stood heap wasm allocator. Cool. Which means that down here, when we look at chamber pixels, we don't have to do any of this like casting shit. We can just do pixel or chamber pixels. Is that what we called it? Yeah. And then I think that's kind of it. It looks like that worked. Why was the build was very fast, which confused me, but it's just that the compile of that was very fast. And then let's use, instead of simple 2, we'll use platforms. Which does not work. So what do? We fucked up save memory, doesn't exist, balls memory doesn't exist, so we have to pull that out. So save memory is equal to return save data. This returns a pointer to U8, I guess, which is working fine. Balls memory is going to do the same thing, which is going to return a pointer to a ball, I guess. And this is balls pointer. And we have the same thing for chamber or canvas memory, which is going to be a U32 output, and this is canvas memory pointer. Okay. Really? Canvas memory pointer does not support. What the fuck? Oh. I'm an idiot. Chamber pixels. All right, so that works. It is not working on the client side. Unreachable executed here when we're trying to render. Pixel data with height. Oh, this is fucking stupid. This shouldn't be passing pixel data. I think I fucked up in simple 2. We still allowed it to pass that in, which we shouldn't have. We don't need this anymore. Right? We should just be using the fucking pixel data directly. Which we have as canvas memory. Canvas memory here and here. Yeah, and then in our index.js, we just shouldn't pass in that anymore, so. Oh, I guess kind of technically, we don't actually need the canvas memory function at all then. Oh, no, we do because we need to copy it out. Right, we do need that. We do need that. We do that. But this doesn't need it. Get chamber pixels. This is still good. Okay, let's try again. It's close. There is, it's writing invalid memory. This is all gray, and we learned last time that the gray was the, like, Zig OXAAs, which is a problem. It looks like the simulation is working there because we can see them bouncing off some platforms and stuff, but it's just that they are not being rendered correctly. So we're just fucking up the rendering. So this is under platforms, Zig, render, chamber pixels. Okay. So here we write chamber pixels. Here we should retrieve the canvas memory, and this is probably working because it's turning gray, right? If this wasn't good, then we wouldn't be returning gray, but we can maybe double check here. Log wasm. Do I have a print function here? Oh, I do. Okay. Canvas memory at this location. And here we can say writing memory at chamber pixels. Chamber, I don't know. Chamber pixels. I guess we take the address of chamber pixels, pixel row start plus X. Yeah. Yeah. Fuck. 34. Oh, because this is still using plugin alloc. Fuck. Wasm, stood, heap, wasm, allocate. Here you go. We got there. Still no good. This doesn't like at 37. This needs to be stood, heap, wasm, allocator as well. Of course. Too few arguments at 183. Really? Oh, at format.take 183, which is coming from. This guy needs to say chamber pixels pointer. I think that's fine. There we go. Okay. Refresh. We look at console. Please let me scroll to where he says writing memory at this location. Fuck. It's too many. Okay, so we'll just kind of start here. We'll see. We'll just look at the chamber pixels themselves. Okay, so we are writing the memory at the right spot, which is a good sign. I don't know why this is crashing here at 102. He doesn't like this. Image data, this canvas width, this canvas height, array. Where does array come from? Get chamber pixels, which comes from pixel data and length. Okay. Where's length coming from? Canvas width times height times 4. Data's coming from the canvas memory. So what the fuck is the problem? What the fuck is the problem? Like here, can we say that we have like data is and length is chamber pixel length. Like, is this working okay? I'll call this canvas memory. What the fuck? Canvas memory is at this address 1114112, which is a lot different than 110000, I will say. Those do look like different numbers, huh? What the fuck is going on there? Is it possible that like this is broken? Is it like that it's returning as an i32 but I'm supposed to cast it back? Give another look at get chamber pixels. This takes in the data and the length from this memory buffer. So this data should just be the exact same value as we see on the zig side, which it's not. Which is concerning to me. So he's calling canvas memory. And this is just returning this value. So let's just see what happens if I try to incast it. Expected integer vector found star 32. Oh, I see. So we need to do point int from pointer. Like this, I guess. Int from pointer, int cast this. I just want to see what happens. Yeah, there's something fucked there, huh? Oh, hold on. Canvas memory at. Hold on. Where was this? We have writing memory here, canvas memory here. Oh, here we are writing chamber pixels pointer. But maybe if I write this as a number, that's different. Because we're also returning the pointer, so I don't see why it would be different. Invalid format type string. Fine. Can we Oh, is one of them hex and one of them decimal? That would also do it. That would do it. So let's try int from pointer here. Oh yeah. Okay, sorry. Fuck. It was this is hexadecimal and this is integer, I guess. And that was fucking with me. Okay, so we're at least reading and writing from the same location, I think. And so now the question is, why is it all gray? Because it shouldn't be all gray. Can we do something like, before we do anything, let's just in index.js go here and not call render, right? Let's assume. Also, this dinit function just doesn't exist, right? Am I fucking high? Oh, no, it does. It does. We didn't remove that. We didn't remove it. Okay, so here, if we go... Kind of interestingly, it's still gray if we don't call render. Which is very surprising. Right, because here we're supposed to get that memory and fill it with FFs. You have the fill in the JS like 992? Yeah, but this should not make it gray. This should make it white. Right? So there's something fucky-wucky going on here. Very strange. Very strange. It's possible that we were like doing invalid memory access before and just not noticing. Okay, so this thing is a uint8 clamped array, and this thing is a image data who has this expected width and height. And we put the image data here. We could maybe like just hit the fucking debugger here and see if we can glean some info here. So on render, can we just like breakpoint here? The server's not running. That would do it. Fine. Breakpoint here. Okay. So what is image data? Data is uint8 clamped array inside. Can I not? Why does this do nothing? So it's uint8 clamped array at 108,000. So I think that 108,000 is probably the WebAssembly module memory. Where do I see this? Exports memory buffer. How do I see? Wait, what was I thinking it was? Oh, sorry. No, it's the size. That's the size. I see. Back here, wherever the fuck we were looking. This is probably saying that it's a uint8 clamped array of this length. Does that make sense? 450 times 600 times 4. Yes, that is the length of the thing. I see. So can we look at this array? No. Oh, here. So his byte offset in this thing is 11.111.4.112, which is the same as this, which is good. So I wish I could fucking expand this shit. Okay, here we go. So here, if we just look at the data in here, it's all 170s, which kind of indicates like zig undefined memory. We have a buffer. This is probably the like WebAssembly buffer. And we are saying we are supposed to be at byte offset here. So I don't see a problem there. Unless like somehow in the image data, it's like fucked in some way. I'm not seeing anything that seems like super wrong to me. It's confusing. Confusing. Put image data. Yeah, it just doesn't make sense. It does not make sense to me. Can we maybe look at, oh, I mean, this fill just must not be doing what we want, right? So if we called array.fill on this with oxff, I mean, we just didn't fill it, right? So there's a bug there. So maybe we should look a little more carefully at what this is supposed to do. Indexing to start the filling of the array at. If it is negative, it's counted as length plus start, where length is the length of the array. Index to stop. So if these are undefined, it should return start to end. And this takes the memory buffer from data to length. Okay. Can we, so if we breakpoint right here, fuck, server's not running again. Is the DNet from the chamber doing anything with the memory? I don't think so, but it's a good thought. I don't ooh, we do free the memory there, huh? That's a good eye. That's a really good eye. Because I think you're right. I think we do free the memory when we do that. Oh, good fucking eye, man. You're a good fucking thought. So here, we should just be able to do this. Put this d init of the thing way down here. I guess we could just put it after the put data because it should copy it out right here. And that should be enough. Oh, that looks really promising. Oh, hell yeah. Let's fucking go. All right. All right. So I think that's pretty good. That brings our like our WebAssembly module interface to be a lot smaller. So can we go to our platforms Zig? So this plugin alloc shit goes away. That goes away. And so now our interface is just, if we were to like copy this and go to like enum, paste it and like delete anything that isn't pub function. Oops. Is it pub export? Pub export function. Okay, so this is our interface, which I think is pretty manageable now, right? I think that it's like pretty reasonable to expect people to be able to implement this, right? So you take in something, you set your static memory wherever the fuck you want for the balls and chambers. Then we have like, I guess we probably don't need a dinit, to be honest. We could probably just leak that shit. Because like on init, we would just like reset. That's fine. Just like we could just say that on it we don't, but we'll leave it for now. It doesn't matter. Then they say, hey, here's my save size and here's where it is located. Here's where you could work with the canvas or the balls and then call save and load step and render. Super straightforward. Super straightforward. Okay, cool. I'm happy with that. That's good progress for today. There's a little more to do there, but that actually that simplifies a lot because like let's see. We can delete now like this WebAssembly allocator as well as the plugin allocator. And if we just like look at the diff stat there, that's like we like deleted like this, we deleted that. I guess the plugin allocator wasn't that advanced, but still feels pretty good. Feels pretty good. Okay, cool. Thanks for watching, guys. If you like what you saw, we're streaming most days at around 2 o'clock Pacific time for around 2 hours. We've started doing like a little bit of a pre-stream that's a little bit more chill and laid back, maybe like an hour beforehand, but the schedule of that will change a little bit probably. Let's see, what else? If you like what you saw, there's a YouTube link in the Twitch description where you can see all of what we've worked on in the past, organized into playlists. Right now we're working on this Rube Goldberg machine, but there's other stuff in there if you want to check it out, like a QR code decoder, operating system, terminal emulator, you know, just kind of like whatever the fuck we feel like ends up in there. There is a GitHub link in the Twitch description as well, where code for this stuff will end up. Like, subscribe, Twitch Prime. Okay, yeah, I think that's it. Goodbye, YouTube and Twitch. Let's find someone to raid.